The transistor. 3 layers instead of 2, 2 junctions instead of 1. A device where one electrical signal controls another. We spent the last episode getting here. Silicon doped into 2 flavors, N-type with extra electrons and P-type with missing ones. Put them together and you get a junction, a diode, a one-way valve. It allows current or it blocks it. That's all it does. But a valve that just allows or blocks isn't enough to build a computer. You need a valve you can control, a switch you can flip electrically, thousands, millions, billions of times a second, with no moving parts. That's what we're building today. There are 2 ways to build that switch. They work on completely different principles. Almost every chip made since the 1970s uses one of them almost exclusively, and by the end of this episode, you'll understand exactly why. Let's start with the first one, the Bipolar Junction Transistor, the BJT. Take our PN junction from last episode and add a 3rd layer. Instead of 2 layers, N and P, you now have 3. N, then P, then N. 2 junctions back to back. Each layer gets a name. The first N layer is the emitter. The middle P layer is the base. The second N layer is the collector. Here's the part that matters. That middle layer, the base, is made extremely thin, thinner than the other 2. And it's lightly doped, meaning it doesn't have very many P-type charge carriers to begin with. Now watch what happens. Forward bias the junction between emitter and base, same as turning on an ordinary diode. Electrons flood out of the emitter, across that junction into the base. Normally, in a P-type region, those electrons would just recombine with the holes and stop. But the base is so thin and so lightly doped that most of those electrons never get the chance. Before they can recombine, they reach the second junction, the one between base and collector, and that junction is reverse biased, which means it's actively pulling electrons through, sweeping them across into the collector. Now think about why that thinness matters so much. If the base were thick, like an ordinary P-type layer, nearly every electron crossing in from the emitter would recombine with a hole before it ever reached the far side. You'd just have 2 diodes back to back, doing nothing interesting. It's specifically because the base is thin enough and lightly doped enough that most electrons survive the crossing. That's not an accident of manufacturing. That's the entire design. So here's what actually happens, end to end. A small current flowing into the base controls a much larger current flowing from emitter to collector. Turn the base current up slightly, the collector current goes up a lot. Turn the base current to 0, the collector current stops almost completely. A small change at the base produces a large change at the collector. That relationship, a small input current producing a much larger output current, is called current gain, and it's what makes a BJT useful as an amplifier, not just a switch. A trickle at the base opens the floodgates for a much larger flow between collector and emitter. That's a bipolar junction transistor, a current controlling a current. One more thing worth knowing, everything we just described used N-type emitter and collector, with a P-type base in between. That's called an NPN transistor, and it's the most common kind. Flip every layer's doping, and you get the mirror image, a PNP transistor, P-type on the outside, N-type base in the middle, working the same way but with the current direction and bias reversed. NPN is what you'll see most in most digital circuits, so that's the one we'll keep building on. Now the second way to build this switch, a completely different structure, the metal oxide semiconductor field effect transistor, the MOSFET. Forget the 3-layer sandwich for a moment. A MOSFET is built differently. You start with a block of P-type silicon, the substrate. Into that substrate you embed 2 separate N-type regions, close together but not touching. One is called the source, the other is called the drain. Between them, sitting on top of the silicon, is a thin insulating layer, an oxide, literally glass, and on top of that oxide sits a metal contact. This is the gate. That oxide layer is the whole trick. It means the gate is electrically isolated from the silicon underneath it, not connected, insulated. A tiny capacitor sitting on top of the channel. With no voltage on the gate, there's no path between source and drain. Just P-type silicon in between 2 N-type islands. Current can't cross it. The transistor is off. Now apply a positive voltage to the gate. Its electric field reaches down through that thin oxide into the silicon underneath, and it pulls the free electrons in the P-type substrate up toward the surface, forming a thin layer of negative charge carriers right under the gate, right between the source and the drain. That thin layer is called a channel, and once it forms, it connects the source to the drain. Current can flow straight through, but it doesn't happen the instant you apply any voltage at all. There's a minimum gate voltage needed, before enough electrons gather to actually form a usable channel. That minimum is called the threshold voltage. Below it, effectively no channel, effectively no current. Cross it, and the channel switches on. That threshold is what makes a MOSFET behave like a clean, decisive switch, rather than something that fades on gradually. Below the line, off. Above it, on. Raise the gate voltage past that threshold. The channel gets stronger, more electrons pulled in, more current flows. Drop the gate voltage back down below it. The channel disappears, and the current stops. Notice what's controlling this. Not a current into the gate, a voltage on the gate. Because the gate is insulated by that oxide layer, almost no current ever flows into it at all. In a resting state, it's close to zero. The gate isn't injecting charge carriers the way a BJT's base does. It's just creating an electric field, and that field does all the work. A voltage, controlling a current. So now we have two switches, both built from the same doped silicon, both able to turn a larger current on or off, but controlled in fundamentally different ways. The BJT needs a continuous base current to stay on, current in, current controlled. The MOSFET needs almost no current at all, just a voltage, held on that insulated gate, doing its job through an electric field, not a flow of charge. That difference sounds small. It isn't. A high-end chip today can hold over 50 billion of these switches, packed onto a piece of silicon the size of your fingernail, each one flipping on and off billions of times a second. If every single one of them needed a steady base current just to stay in the on state, the power draw and the heat would be enormous, unworkable at that scale. A MOSFET sitting there with its gate voltage held high draws almost nothing, just enough to charge that tiny gate capacitor each time it switches. That's the entire reason modern computing is built almost exclusively on MOSFETs, not BJTs. Not because BJTs are worse, they're still essential in amplifiers, in radio circuits, in power electronics, but for packing billions of switches onto one piece of silicon the size of your fingernail, the MOSFET wins. Voltage control, near zero standing current, and a structure that shrinks beautifully as manufacturing gets more precise. Strip away all the physics for a second, and here's what both of these devices actually are. A switch with a third terminal. Apply the right signal, a base current or a gate voltage, and current flows freely from one side to the other. That's on. Remove that signal and the path closes. No current. That's off. On, off, a voltage that's high or a voltage that's low. Two states. Only two. Not a dimmer switch, not something in between. Because of that threshold voltage we just talked about, a MOSFET snaps decisively from one state to the other. And once you can represent those two states reliably, electrically, switching billions of times a second, you're not just building a valve anymore. Call that high voltage a 1. Call that low voltage a 0. You're building the physical foundation of every 1 and every 0 a computer will ever process. Every number, every letter, every instruction, every image, all of it, eventually, coming down to transistors like this one, flipping on and off. We have our switch. Now we need to teach it to make decisions. In the next episode, we take a single transistor, wired the simplest way possible, and build the first logic gate, the NOT gate. One input, one output. A circuit that takes a signal and flips it. It's the smallest possible piece of logic. And every other gate, and or everything a computer will ever compute, gets built starting from ideas exactly like it. The switch is ready. Now it starts to think.